Greetings. In last lecture, we discussed about deflection of determinate frames, where we have used Castigliano first theorem to know the deflection caused by the applied force in a given system, which states that if we take a derivative of the total strain energies possessed by a system with reference to the applied load, we can get the displacement due to that applied load. This concept was utilized to find out the deflection in trusses, where we consider trusses member are axially loaded member which are having a gradual loading system over it, and based on that we have come to a relationship like di by equals to summation of fi ki li divided by e, where fi is nothing but force in the member due to applied load f, and ki is nothing but the force in the member due to unit load applied instead of the applied force F, and Li is the member length, and AE is nothing but axial rigidity. Let us solve some numerical based on this concept. Let's begin with numerical number 1, which states that determine the deflection of the joint B shown in figure. Take AE as a constant. The given frame is a cantilever frame which is supporting a vertically downward load 20 kN at joint B. Joint A and C are on vertical wall at a distance of 2 meter, whereas the distance between the joint B and C is 2 meter. From the geometry we can say angle B is of 45 degree. To find out the deflection at joint B, what I have to do, I have to find out the forces in the member, then I have to apply a unit load at the joint B instead of the applied load 20 kilonewton, and then I have to find out what is the coefficient of distribution of that force, unit force, among the member, and the product will define as the deflection caused at the joint B due to the given loading system. Let's begin with the force analysis. First, we will prepare free body diagram for the joint B, where two members are going to meet and a applied load is there. Applied load is 20 kilonewton. Let us consider member AB. FAB is the force generator, which is tensile in nature to counterbalance the downward moving load. Here FBC is having a compressive force. Member FBC is going to have compressive force to counterbalance the force in member AB. Now I will apply static equilibrium equation to the joint B. Summation of Fy equals to 0 yields to the relation FAB sine of 45 minus 20 equals to 0. Means for vertical component of this FAB force will be sine component, because angle is traced with the horizontal axis. It is going to balance the 20 kilonewton load which is going downward. This results into FAB is equals to 20 divided by sine of 45, which comes to 28.28 kilonewton tensile in nature. Now I will go with the second equation, summation of forces in x direction equals to 0, which results into minus FAB cos of 45, cos component of this AB force, plus FBC, which is going towards the right hand side, equals to 0. From this we can say FBC equals to 20 kilonewton compressive in nature. Now I will move towards the K analysis. For that, what I will do, I will replace this 20 kilonewton load with a unit load, and we'll find out what is the statics with reference to this applied load. Now again I will apply static equilibrium equation for the consider signs for the forces in the member. Summation of Fy equals to 0 will yield into Kab sine of 45, means Kab sine of 45 vertical component balancing the unit load minus 1 equals to 0 yields into Kab value as 1 by sine 45 1.414 kilonewton tensile in nature, and summation of forces in x direction equals to 0 yields in the relation minus Kab cos 45 cos component of this Kab force plus Kbc moving towards right hand side, resulting into Kbc value as a 1 kilonewton. After knowing the forces F forces and K forces, I will put this results into tabular format, which will be related with member length, force Fi in the third column, force Ki in the fourth column, and product Fi Ki Li. So for member AB we have length 2.828 and force in the member is minus 28.28, minus sign for the tensile nature. Force in Ki is minus 1.414, result into 113.08. For member BC, length is 2 meter, force is 20 kilonewton, and Ki force is 1. Compressive forces, that product is 40. The summative value is 153.08. If I want to write in terms of deflection, we can write summation of Fi Ki Li divided by E is nothing but the total deflection caused under the applied load, which results into 153.08 upon E. Now let us move to the numerical number 2, which has a statement: determine the vertical and horizontal deflection at C of the structure shown in figure. All members have same axial rigidity. The frame is given to us having two supports, one at A hinge support and at B there is a roller support. The frame is going to support a vertical applied load 20 kilonewton in vertical direction and a horizontal load towards the right hand side 10 kilonewton at the joint C. Also at this joint C we are interested to know what is the deflection caused by this external loading system. For that, first I will try to classify the structure, whether it's a determinate or indeterminate. For that, I will first find out the unknown reactive forces. From given end resistance, we can say there are three unknown reactive forces, two at joint A and one at roller joint D. Now, if I count the number of member count is 5, number of joint count is 4. If I put this into relation for static indeterminacy, m plus r minus 2j, it yields into 5 plus 3 minus 2 into 4 comes to be 0. It means it is statically determined. Once I came to know it's a determinate one, I will apply static equilibrium equation for the global geometry to find out unknown forces. For that, summation of fx will result into minus ha plus 10 equals to 0, 10, and the HA is going towards the left hand side. From this, HA comes to be 10 kilonewton moving towards left hand side. Now I will apply vertical equilibrium here. Summation of forces in vertical direction equals to 0, result into RA plus RD, RA plus RD going upward and 20 kilonewton coming downward equals to 20. And now I will utilize this third equation, summation of moment about the joint A. I will take moment of all forces about the joint A. 20 into 3, it is going to have a clockwise turn here. 30 into 4, it is again generating a clockwise twist here, which equals to 3 into RD. RD is going to create a anti-clockwise twist here. That's why 3 into RD. From this relation we get RD equals to 33.33 upward. Now we'll substitute this relation back into the first equation, RA plus RD equals to 28. From this what we get, RA equals to minus 13.33. Means what? Minus sign says the assumed direction is wrong. We have to change the direction here. The consideration will be towards downward. So that's why what I will do, I will make the changes in the figure. I will revert the direction towards the downward. After knowing the reactive forces, what I will do, I will try to find out the unknown member forces here due to applied loads on it, applied forces on it. So let's begin with the F analysis. I will call that as a F analysis. To begin here with, I will first find out geometric constants here. Let us find out angle traced by the member, inclined member here. From the geometry ADC means triangle ADC, I can get theta is equals to tan inverse of CD divided by AD, which equals to 4 by 3, 53.13. To fasten the calculation, I will first calculate the sine component and cos component here. So sine theta will be resulting at 0.8 and cos theta will be resulting into 0.6. Now I will go with a joint by joint analysis. Now joint B, I have to move with a joint which is having minimum two unknowns. There are two possibility here, either go with B or D. I will move with a B joint. So joint B, if I take equilibrium your free body diagram here, so FBC and FBA are the forces in the member, but there is no external load to apply it. That's why from a static equilibrium equation we can say summation of Fx equals to 0 yield into FBC minus 0. No applied force is there, hence FBC equals to 0. Similarly, summation of Fy is equals to FAB minus 0 means there is no external forces. FAB will be equals to 0. Now I will move to the joint C. Joint C, if I prepare free body diagram, there are four forces here. 20 kilonewton applied force going downward, 10 kilonewton applied force moving towards right hand side. And to have equilibrium in the forces, I am considering the assumed direction here. FCD is going to be in compressive nature and FCA is going to be in tensile nature. After this, I will apply static equilibrium equation for this system here. So summation of force in x direction yields to be FBC minus FCA cos of theta minus 10. The FCA will have cos component with horizontal here. FBC is 0, and from this relation we can get FCA is equals to 16.67. Now if I use the vertical equation, summation of vertical forces is equals to 0, we get a relation FCD minus FCA sine of theta minus 20. FCA will have sine component with vertical axis, 20 kilonewton is going downward, both are negative, and FCD is going to be upward. We know the value of FCA. If we substitute here, it yields to be FCD equals to 33.33 kilonewton. So from joint C, I am going to get two unknown forces, that is force in member AC and force in member DC. Now I will move to the joint A. Towards the joint A, what I am getting here from figure free body diagram, four forces are there. 10 kilonewton horizontal reactive force, RA 13.33 kilonewton. FAC just we have find it is a tensile in nature, and for the balance I am going to consider FAD is compressive in nature. Only one force is there, that's why I will consider horizontal equation, equilibrium of horizontal equation here first. Minus FAD plus FCA cos of theta minus 10, this will result into value of FAD equals to 0. If I move with a vertical relationship, the summation of y equals to 0 yields into FCA, sine component will be there minus RA. So this will be resulting into 0, means what we have gone for a what we say equilibrium analysis here. So with this I can say F analysis has been completed. Now since in numerical it's stated that we have to find the deflection in both the axis, horizontal displacement well as vertical displacement, what I will do, I will prepare K1 analysis where I will apply unit load in horizontal direction, let us say towards right hand side, and second case I will apply a unit force in vertical direction, let us going to be upward. Now with this I will start with the K1 analysis. For before K1 analysis, what I will do, I will first find out the reactive forces with reference to end resistance. If I apply summation of force in x direction, it yields into minus HA plus 1 equals to 0. HA comes to be 1 kilonewton. If I go with the vertical direction, so it will be RA plus RD equals to 0. Since there is no vertical loading here, RA is equals to RD, but opposite in nature, opposite in direction. Now if I apply summation of moment about the joint A, 1 into 3 will be the twist here, which is going to 1 into 4 will be the twist created by unit force, and 3 into RD is the twist created by reactive force. It will result into RD equals to 4 by 3, which comes to 1.33 kilonewton going upward. Then RA will be the opposite to that 1.33 kilonewton going downwards. I will go move with a joint by joint analysis for the K1. So here if I will start with the joint B because two unknowns are there. There is no external forces. That's a summation of force in x direction will yield to be to the value of member forces. I will represent value of member forces as a K because I am going to consider unit load, and coefficient I am going to consider KBC equals to 0, and summation of Fy KAB minus 0, KAB equals to 0. Now I will move to the next joint, joint C. At joint C I am having three unknown forces, three forces here. 1 kilonewton KAC coming, I am considering it as a tensile in nature. KCD I am considering it as a compressive in nature. If I apply summation of forces in x direction, it yields to minus KAC cos of theta plus 1, resulting to KAC equals to 16.67 kilonewton. The summation of Fy is equals to KCD minus KAC sine of theta equals to 0, resulting into KCD equals to 1.33 kilonewton. With this I think all member forces related to C joints are being find out. Joint A, if I go with the joint A, there are three unknown forces. Among these two are, there are three forces acting, two are known to us, only one is unknown. Let us apply summation of forces in x direction to get this unknown. KAC cos of theta, the horizontal component, plus KAD minus 1, this will result into KAD equals to 0. Now from this I will say K1 analysis has been completed. Now we will move to the K2 analysis. The same procedure I will follow for the equilibrium equations. From that we will find the reactive forces first. The reactive forces come to be RD equals to 1 kilonewton, R equals to 0, and HA equals to 0. Now if I move the joint by joint analysis, joint B will result into KBC equals to 0, KAB equals to 0. Joint C analysis will show that the forces in member KAC is 0 and member KCD is equals to 1 kilonewton. Similarly, if we move to the joint A, we will get the answer KAD equals to 0, means here all four members are having 0 forces, and only one member is going to have 1 kilonewton force, which is in tensile nature. I will substitute it into a tabular format where I will prepare a table first with member length followed by force in Fi, force due to applied loading, force due to unit load, K1 analysis, K2 analysis, then the product. So I will put individual values here. AB length is 4 meter, BC 3, CD 4, DA 3, AC 5, and the forces in the member 0, 0, 33.30 minus 16.67. Force due to K1 0, 0, 1.33, 0, 1 minus 1.67. Force due to K2 0, 0 minus 1, 0, 0, and product will yield as to be summation of Fi K1 I Li is 316.89. Summation of Fi K2 I L is minus 133.32. If I want a deflection in horizontal direction, summation of the value for horizontal force divided by A will result horizontal deflection, whereas for vertical deflection, summation of Fi K2 I L means unit load in vertical direction divided by A will result in the vertical deflection. With this, I will end with the session and will come with some more numerical. Till that, be safe, be stay at home.